We will now move on to the details of how the Anova test works. I need to introduce a few more terms here. K is going to be the number of groups. In our case, we're going to have 6 groups for our smoking example. N sub I is going to be the number of observations in group I. N is going to be the total number of observations. It's going to be N1 plus N2 all the way down to N sub K, where there are K groups. That's going to be the total number of observations. Y sub I bar, we already know, is going to be the sample mean for group I. And S sub I bar, or S sub I, sorry, is the sample standard deviation of group I. Okay, so let's start with the deviation of an individual observation from the overall mean. We looked at this once before, y sub I j minus y bar. How far is one individual from the overall mean? Well, we're going to break this into 2 pieces. We're going to do y sub I j minus y sub I bar. Then we're going to add back y sub I bar and then subtract y bar, so that we break this up into the deviation of an individual from its group plus the deviation of the group from the overall mean. Now I'm going to define what's called the total sum of squares. So I'm going to square both sides and sum over all observations and groups. Okay, so the total sum of squares, I want to sum all of the y sub I j's minus the y bars. Okay, so that's going to require me to sum over all individuals within a group, j equals 1 to n sub I, and then I'm going to have to sum over all the groups from I equals 1 to k. That way, when I'm summing, I get all of the y sub I j's. And I'm going to take that, subtract y bar squared. So this can actually be squared and then broken up into 3 terms. Okay, so if I square that, there's the I equals 1 to k, j equals 1 to n sub I of y sub I j minus y sub I squared. Okay, so I'm looking at squaring this term right here. Okay, it's got 2 pieces. And then I'm going to sum from I equals 1 to k, sum from j equals 1 to n sub I, and I'm going to sum y sub I bar minus y bar, quantity squared. And then when I square these 2 terms, okay, I'm going to have these cross terms, 2 sum from I equals 1 to k, sum from j equals 1 to n sub I of y sub I j minus y sub I bar times y sub I bar minus y bar. So just so you understand, okay, I basically took a plus b squared and said that that's equal to a squared plus b squared plus 2ab. Okay, I specifically want to look at the 3rd term. Okay, so I've got that double sum, and then I have y sub I j minus yi bar times yi bar minus y. And I want to know what happens with that. Okay, so first I'm going to notice that the y sub I bar minus y bar, this part right here, that does not depend on j. So I can actually pull it out of the sum. Okay, what's left inside the sum is then the sum from j equals 1 to n sub I of y sub I j minus y bar. Now, what is y sub ij minus y bar when I take the sum of that? Okay, so first, what is the sum of y sub ij from j equals 1 to n sub I? If I just sum up all of the data, well then that's n times the average. We've used that technique several times before. But now I'm also going to sum y sub I. Y sub I there is a constant with respect to that sum. So I'm going to sum the same constant n sub I times. And so I'm going to get minus n sub I yi bar. Well, n sub I yi bar minus n sub I yi bar, well, that happens to be 0. Aha. What does that mean? That means this whole term is 0. Okay, that means we can write the total sum of squares as only having 2 pieces. Okay, so we have that the sum from I equals 1 to k, sum from j equals 1 to n sub I of y sub ij minus yi squared plus the sum from I equals 1 to k, sum j equals 1 to n sub I of yi bar minus y bar squared. So the total sum of squares is equal to the sum of the squares of those 2 parts. We call those things SSE for sum of the squares of the air, and SST for the sum of the squares of the treatments. Now, by treatments, they mean groups. Imagine that we were giving 4 or 5 different groups different treatments for a disease. Then we would be looking at all those groups and seeing if there's differences between those groups. Okay? Or we could be treating some sort of substance with another substance, and there would be different treatments that we could use. So you can see that the language here really probably comes from biological experiments. Okay, in our case, the treatments are the different smoking levels. Obviously, treatments is not a good word in this case with the smoking levels, but that is the terminology that this book uses and a lot of software uses. Okay, so the sum of the squares of the air, that's going to be the within group variability. So it's the within group variability. You'll notice that I'm taking the sum of the squares of the y sub ij's, so observations minus their own group mean. So that's how much things are varying within the groups. Okay, and then the second term is going to be the between the group variability, or the treatment variability. Okay, so let's move on. Okay, so total sum of squares is going to be the sum of the within group variability and the between group variability. 2 important factors for our Anova test, as you saw from some of the diagrams that I did in the last video. Okay, so the total sum of squares measures the overall deviation of the data from the mean. We saw that it's composed of two parts. The total sum of squares is the sum of the squares of the error and the sum of the squares of the treatments. Sum of squares error we can look at as the sum from I equals 1 to k, and it's the sum from j equals 1 to n sub I of yij minus yi bar squared. And if you look at that very closely, you can see that what's on the inside here, this looks like part of our variance formula. So in fact, we can sum over the groups. And that, if we had divided what's outlined in red there by n minus 1, then that actually would be the variance. Okay, so what's there is actually n minus 1 times the variance for each group. And so that's another way that we can write the sum of the squares of the error. Okay, so you can see it's a linear combination of the variances. Now, what about the sum of the squares of the treatments? Okay, so we can write this as the sum from I equals 1 to k, sum from j equals 1 to n sub I, and this is yi bar minus y bar squared. And you'll notice that that term, as we saw before, is constant with respect to the j sum. So, in fact, we can write this as the sum from I equals 1 to k of n sub I times yi bar minus y bar squared. And that's a really nice simplification of the sum of squares treatments. That's one formula that we could use, but there is another one that the book tends to use. So I'm going to write this as the sum from I equals 1 to k of n sub I times, and I'm going to write this as yi bar squared minus 2 yi bar y bar plus y bar squared. And then I'm going to break this up into three sums. The sum from I equals 1 to k of n sub I y bar yi bar squared minus 2y bar sum from I equals 1 to n of n sub I yi bar plus y bar squared times the sum from I equals 1 to k of n sub I. So now broken that up into three terms, and anytime I could take a constant out, I did just that. Okay, so this is now, I'm going to repeat the first term, the sum from I equals 1 to k of n sub I y sub I bar squared minus, okay, so I'm going to get a 2y bar, and then when I'm looking at this sum, if I sum n sub I yi bar, well, that is a linear combination of the means. If I had divided that by n, that would just be y bar. So what I have there is actually ny bar. And then plus, if I look at this term, the sum of the n sub i's, that's just n. Okay, that's the total number of observations. So I'm going to get an n bar squared. So this becomes the sum from I equals 1 to k of n sub I y sub I bar squared minus, notice that I have one of these, and then I'm subtracting two of them, so I'm going to get just minus ny bar squared. Okay. Now, assuming that our y sub ij's are normal and have about the same variance, that's actually very, very important. So we need to have approximate normal distributions for our populations, and they have to have about the same variance. Okay, the sum of the squares of the error, okay, which you can see is just a linear combination of the variances, right? That's going to have a chi-square distribution, and it's going to have a degrees of freedom of n minus k. Okay, the derivations for these are a little bit difficult. The book does this for two groups. So if you want to look at it, the book does this for two groups. But basically, these derivations are similar to when we first were looking at the chi-square distribution, specifically for comparing variances and looking at confidence intervals for variances. Okay, so that's where all this comes from. So you'll have to kind of go back to look at the beginning of this course to see why this has a chi-square distribution. It's very, very similar to when we were looking at comparing variances or doing confidence intervals around variance. Okay, so that sum of squares treatments, you can see, well, that's a function of y bar and y sub I bar. Those are normally distributed, but they're squares again. And so this is actually going to also have a chi-square distribution. It has a similar derivation as for the sum of squares error, and that has degrees of freedom of k minus 1. But it's important that all the groups have approximately the same variance in order to get those chi-square distributions. Okay, now we're going to look at what's called the mean square for error and treatments. So I want to take the sum of the squares of the errors, and I'm going to divide that by n minus k. When I do that, I'm going to get the sum from I equals 1 to k of n sub I minus 1 s sub I squared over n minus k. So what I have here is a weighted average of within group variances. So I've taken a linear combination of variances based on their group sizes, and I'm dividing that by the total number of degrees of freedom. If I add up all the degrees of freedom for the different groups, then I'll get n minus k. So this is a weighted average of the group variances. That's what we call the mean square error, weighted average of the within group variances. Now the mean square treatments, we're going to divide that by, the sum of squares treatments by k minus 1. Okay, so that's going to be the sum from I equals 1 to n of yi bar minus y bar squared. And I also need an n sub I in front of that. And I divide that by k minus 1. Now that is actually going to be a weighted average of the between group variances. You can see that for each group, I'm taking the sum of the group size times the variance of that group mean minus the overall mean. And so that looks like a variance formula where I'm doing the variance here for the groups. So it's a weighted average of the between group variances. Okay, now we could rewrite this if we want using that formula we found, sum of I equals 1 to n sub I, y sub I bar squared minus ny bar squared. And then we divide that by k minus 1. Okay, so mean square treatments is between group variances, and mean square error is within group variances. Those are the two things that I said that I wanted to compare. I wanted the between group variances to be larger relative to the within group variances. And so what we're going to look at is we're going to look at the quotient of the mean square treatments divided by the mean square error. And the reason is the mean square treatments has a chi-square distribution, and the mean square, the sum of squares treatments has a chi-square distribution. The sum of square errors has a chi-square distribution. And so if we take those two chi-square distributions and we form a quotient where we're dividing by degrees of freedom, that has an F distribution. And here the numerator degrees of freedom is k minus 1, so it's the number of groups minus 1. And the denominator degrees of freedom is n minus k. So if you go back and look at where we introduced the F distribution, then you will see that we had a quotient of chi-squares which each were divided by their own degrees of freedom. Okay, so now it makes sense that we're going to be comparing the between group variances to the within group variances, and we now know what the distribution is when we do that comparison if we form a quotient. Okay, so let's remember what our hypotheses are, okay? The hypotheses are that each of the mu's are equal for the null hypothesis, right? All the group means are equal. And then the alternative is that they are not all equal, okay? At least one mu sub I is different. Okay? And the basic idea is that we're going to reject the null hypothesis if the variability between treatment groups is sufficiently larger than the variability within treatment groups. Okay, our F statistic is we're going to take the mean square treatments and divide by the mean square error. And if the mean square treatments is much larger than the mean square error, then F sub S is large. Okay, and between group variability is much larger than the within group variability, so the groups will be clearly distinguished as having different means. That was that first picture that I had showed you. But if the mean square treatments is much smaller than the mean square error, then F sub S, our statistic, is going to be small. Okay, so if mean square treatments is small relative to mean square error, then the means are going to be difficult to distinguish. And that was that second picture that we had. There's too much variability within the groups, so it's difficult to distinguish them statistically. Okay, so therefore, if our F sub S, which is our test statistic, is bigger than F sub alpha, then we're going to reject the null hypothesis. So our rejection region is F sub S greater than F sub alpha. And if we can do that, we conclude at least one mean is different from the others. Okay, and note that when you run this test, okay, it's a test where we're going to run f sub s greater than f sub alpha. Okay, so please note that this is not going to be f sub alpha over 2. Okay, so this is going to be a directional rejection region. Okay, so I'll write this here. Rejection region is f sub s greater than f sub alpha, or f greater than f sub alpha. Okay, so this will be very similar to when we've used that kind of rejection region before when we were comparing variances. Okay, so most of the time you're gonna want to run this kind of test in software. I'm going to show you how to do one by hand, but most of the time you will run this kind of test using software. And usually the software will give you a table that looks like the one here. So they'll tell you the degrees of freedom for treatments and for air, and then the total degrees of freedom, which is just n minus 1. And they'll give you all of this information: sum of squares treatments, sum of squares air, okay, and then the total sum of squares which is the sum of the two sum of squares that I've underlined. It'll give you the mean squares treatments and the mean square air. It'll give you the F statistic, and then usually it'll give you the p-value, so the probability that F is bigger than your F statistic. Okay, and that's usually what you would get out of software when you're looking at a one-way Anova test.